Today we will continue with our discussion about data mining. So far we've finished discussing chapter 10, which is about two population hypothesis test, and now we will proceed to one-way analysis of variance, which is chapter 12. Now what's the main difference between the two? As we can see here in this matrix, two population hypothesis test is for qualitative and quantitative, and that's the same for one-way analysis of variance. So when do we use this and when do we use one-way analysis of variance? As discussed last time, two population hypothesis test is used to find relationships between a quantitative variable and a qualitative variable. But qualitative variable needs to have just two treatments only, meaning the possible values or the unique responses for the qualitative variable are just two. And examples of this last time were the gender, the state of the dogs, if they were asleep or not, and then the cars, if the customer brought a car with them or not. And since this is a two population hypothesis test, again, we can try to test if the average of the first population is greater than, less than, or not equal to the average of the second population. Now for chapter 12, which is about one-way analysis of variance, this is now used to find relationships between a quantitative variable and another qualitative variable, but this time the qualitative variable has more than two or at least three treatments. So effectively it makes us have more than two populations, and P here represents the number of treatments or the number of possible values or the number of unique responses for the qualitative variable. Now, one-way or single-factor analysis of variance, or simply ANOVA, is also a certain kind of hypothesis test. Therefore, we have the null and the alternative hypotheses as well. Now, according to the null hypothesis for one-way ANOVA, we are trying to see if the average of the first treatment is the same as the average for the second treatment up to the last treatment. And then for the alternative hypothesis, we are trying to find if at least two of these different means differ. Okay, so that's one limitation of one-way ANOVA. It will not tell us directly which of the means differ. It will just try to find out if at least two of all the treatment means that we have or that we are testing are different from each other. So a more concrete example of this would be, let's say you're trying to compare the average amount spent of students coming from different schools in Katipunan. So maybe MUSUB 1 can refer to the average amount spent of students from Ateneo. MUSUB 2 is the average amount spent of students from Miriam, and so on. Okay? So if you perform a one-way analysis of variance there in that scenario, then you can try to identify if there are at least two averages that are different. So maybe the values or the averages for Ateneo and Miriam are different, or maybe Ateneo and UP are different, or Miriam and UP. And again, the limitation of ANOVA is that it will not tell us which of the two differ. We'll just know if at least two of the different means are different, significantly different, statistically different. Okay? Now, similar to two population hypothesis tests, the one-way or single-factor ANOVA is only valid if twice the smallest treatment standard deviation is greater than the largest treatment standard deviation. So there are also a lot of other assumptions for one-way ANOVA, but we won't be discussing that anymore because one-way ANOVA is relatively robust, meaning even if some assumptions are not satisfied, the results will still be accurate. So the minimum requirement for ANOVA is this: compute for the standard deviation for each treatment and then compare them later on. And again, if twice the smallest standard deviation is greater than the largest treatment standard deviation, then the one-way analysis of variance will be valid. And in terms of data preparation, it's also very similar to population hypothesis test. Here, one column should be devoted to one treatment. So similar to last time where we have one column per population, here we also have one column per population again, for the population for each treatment. Okay, so that's it for one-way analysis of variance. Okay, now let's try performing the test using Excel and using StatPlus, using the two databases that were uploaded in the group. So first, again, we have here the database for Barkin Blends. So this is the same database that we used in class. So let's say in this scenario, we were asked to try to find a relationship between the amount spent and the monthly household income. Okay? So again, first, why can we use one-way analysis of variance for this? Monthly household income, again, inherently is quantitative, but again, as we can see here, they are limited to intervals, so this effectively becomes qualitative. And in terms of the number of treatments, we have more than two possible values. So we have 30 to 60, we have 60 to 90, we have 90 to 120, and so on. So since we have more than two treatments here, then this can be something that can be used for one-way ANOVA. And then the other variable is amount spent, and as we can see here, amount spent is quantitative. We have the actual values. So again, for us to test the two, we can use one-way analysis of variance. So similar to what we did before, copy and paste the two variables to another worksheet. And then once you have it in another worksheet, the next step is to sort it, okay, to prepare the data before we start running the tool. So again, to sort this, there are lots of ways for you to do this, but for me, I'll just try to sort in terms of monthly household income so that it will be arranged in terms of the income. So for the first one, 30 to 60, so I'll just copy all the values of 30 to 60 in one column, and then followed by 60 to 90. And then after 60 to 90, we have 90 to 120. And then greater than 120, that's this one. And then finally, we have less than 30. Okay. If you want, you can also arrange it in terms of the proper order, because remember, this is ordinal. So technically, less than 30 should come first. But again, it doesn't really matter because these treatments, once they are separated into different columns, then they're already treated as different treatments or different populations. So here we can add the column headers so that later on it will be easier for us to interpret them. So it's 30 to 60,000, 60 to 90,000, 90,000 to 120,000, and then this is greater than 120,000, and then the last one is less than 30,000. Okay, so again, even if the number of treatments are not, number of responses for each treatment is not the same, most of the time the results of the ANOVA will still be valid as long as the test that we mentioned earlier is satisfied. So ideally, it will be good if you have equal number of treatments for equal number of responses for each treatment. But again, even if that is not the case, we can still be able to test the variables. So now that we've sorted, now that we've prepared the data, then we can now start performing one-way analysis of variance. So here, I'll use StatPlus. So for the process is very similar for StatPlus and then for data analysis 2-pack. So for StatPlus, click statistics, and then instead of basic stat and tables, now proceed to analysis of variance, and then choose one-way ANOVA. Okay? For Excel users, so again, it's the same process. Click data analysis at the upper right part, and then the dialog box will appear showing you different functions, and then there choose one-way or single factor ANOVA. And then here for StatPlus, once I select this, another dialog box will appear, and then here I just have to make one selection. I have to make one big selection for the column header until the last response for all the treatments. So I just have to make one selection. For Excel, I think you have to do something similar. So you have to make one selection, and then you have to choose the option where the treatments or the populations are divided in terms of columns instead of rows. And then since we also highlighted the column headers, make sure that this part here is checked, yung labels in first row. And then once you're done, just click OK. And then another worksheet will appear showing us the results. So this is how the analysis of variance results will look like. I think it's also very similar to the output for Excel. Now, again, as mentioned earlier, for us to know if the responses are valid, we have to perform a certain kind of test. But before that, let's try to look at the results of the test. So we have here the different treatments, 30 to 60, 60 to 90, and so on. And then we also have here the sample sizes. So majority of our responses had greater than 120,000 monthly household income, and then the least is for 60 to 90. And at the same time, we can also see the mean and the variances for the amount spent. So as we can see here, 220,000 is the highest, and that is for the monthly household income 90 to 120,000. And then the smallest is for 60 to 90,000, which is 187.5. And again, even if the sample means that you obtained here are different from each other, it's not a guarantee that the actual averages for all the different customers coming from different treatments are actually different, because remember, you're just getting information from a sample. And now for us to know if the test will be valid, we need to compute for the standard def. And since we already have the variance here, then we can just compute for the square root so that we can get the standard deviations. Okay? So now we have the standard deviation. So if you want, you can add here column header standard deviation. So we have the different standard deviations for the treatments. Now, the rule specified earlier is that the test will only be valid if the smallest times 2 is greater than the largest. And if you look at all the standard deviations here, the smallest is 23.7171. And again, if you multiply this by 2, you have to compare that to the largest. And the largest standard deviation here is 69. Now, since twice is still less than the largest, then according to the rule, the one-way analysis of variance is invalid. So you can't really perform the test. So when you arrive at this situation when the test is not valid, there are some other ways for us to fix it. First, maybe you can get more responses. Maybe if you have equal responses for different treatments, maybe the variances will be very similar. Or one quick way for us to try to fix this is maybe we can try to combine certain treatments. So if you look at this, 60 to 90 just has 10, and then 90 to 120 is 18. Maybe we can combine the two, and possibly if we combine the two, the standard deviations of the two will now be closer to the other values. Okay, so how do we do that? So first we can close this, and then going back to the data set that we had earlier, again we will combine 60 to 90 and then 90 to 120. So I can cut this, paste this to this side, change the upper limit from 90 to 120, and then we can just delete this. So now we have just 4 treatments. So it's still possible for us to perform one-way ANOVA. So now let's perform one-way ANOVA again. So one-way ANOVA, and then make another selection. So press OK, and then now the worksheet will appear. So here we now have just 4 treatments. The treatments are still mutually exclusive. And now let's compute for the standard deviation. So just get the square root of the variances. And now the smallest is 44. And if you multiply this by 2, this is now greater than the largest, which is 69.988. And because of this, the results of the ANOVA will now be valid. Okay? So after this, we can now proceed to the next one. And here, in the ANOVA table, we can now make inferences. Okay? And again, there are lots of ways for us to interpret, but the easiest way is just by looking at the p-value. And here, the p-value is 30.86%. And again, this is using the p-value method, so we only reject the null hypothesis if the p-value is less than alpha. But again, the p-value that we have here is too high, which means that, again, following the same process, we don't have enough information, or there's insufficient evidence for us to support the claim that at least two of the different means are different. Or in this case, we don't have enough evidence to support the claim that the average amount spent from different monthly household incomes are different. Okay, so we don't have enough evidence to support the claim that at least two of the different average amounts spent coming from different monthly household income differ. So that's how we interpret this result for one-way analysis of variance. Okay? Now we can try another set of variables. So instead of park and blends, maybe you can use the other one. Let's try to use the Rustans Katipunan database. Now, let's say we are asked to test the variables house type and then the number of people in the household. Okay? House type and number of people in the household. So again, similar to what we have been doing for the previous variables, let's copy those variables and paste it to another worksheet. So here, that's the house type. And then here, we have the number of people in the household. So once you've segregated them, isolated, again sort so that it will be easier for us to prepare the data. So sort according to the house type. So we have different treatments here. The first one is for apartment, followed by condominium, and then we have dormitory, and the last one is own house. Okay, so again we can add the column headers: so apartment, condominium, dormitory, and own house. So now that we have finished organizing the data, we can now perform one-way analysis of variance. So again, for StatPlus, that's ANOVA, one-way ANOVA. For Excel, that's data analysis, and then single factor ANOVA. And then here, I'll select all the data. And then press OK, so the other worksheet will now appear. So these are now the results. So again, we have 4 different treatments. We have here their sample sizes and then their average. So here, as we can see, the average number of people in the household for the different house types are different. So we have 5.5 for own house, we have 4.6 for apartment, and then the smallest one is for the dormitory. And again, for us to check if the results will be valid, we compute first for the standard deviation of the different treatments. So this is the smallest. And then if we multiply this by 2, this is now bigger than the largest standard dev, which makes, again, the test valid. And now, since the test is valid, we can now look at the p-value. And looking at the p-value, this is very small. In fact, this is smaller than 0.001 or 0.1%, which means that, again, using the same process, we have extremely strong evidence to support the claim that the average number of people in the household from the different house types differ. Okay? Again, we have extremely strong evidence to support the claim that at least 2 of the average number of people in the household differ from the different house types. Okay? Now again, the limitation of ANOVA is that it won't tell us which exactly differ. So we can't really tell if the difference is between apartment and condo, or apartment and dorm, or condo and own house. But again, ANOVA just tells us that at least 2 of them are different. Now, for the test to make more sense, you can actually perform a t-test, pairwise t-test among the different groups. So segregate the values for apartment and then condo, and then perform a t-test, and then try to check which one is smaller, which one is greater, and then do the same for the other categories. And then there, if you perform different t-tests, then it's now more valid. You can now actually identify which of the tests differ, or which of the averages differ, or the averages different between apartment and condo, apartment and own house, and so on. Again, you can also do that using the first one that we discussed last time, which is about two population hypothesis testing. Okay, so normally after performing ANOVA, we also perform two population hypothesis tests for us to really know which averages differ. Okay, now that we've uh, identified the p-value and we've made the necessary interpretation, again, one other step usually is to try to identify exactly which means are different. So if the different is caused by the apartment and the condominium, apartment and dorm, or apartment and own house, or something else. And for us to do that, ideally we have to test all the different pairs. So do that for all the possible pairs here. So again, apartment and condo, apartment dorm, or condo and dorm, condo and own house, and so on. Okay, so you won't be doing that here in this video. You can just try to do that on your own. I'll just try to show you how to do it for the first few. Now, let's say you want to test apartment and condo if the values are different for the two. So again, as mentioned earlier, you can use the t-test for that. So we have already segregated the different treatments here. So if you look at apartment and condo, we have all their respective values. However, if you count the number of values for apartment, that's only 13, and then for condo, that's only 19. The problem here is that it doesn't really satisfy the condition. So the sampling distribution for both are not really proximity normal because you don't know the distribution of the population, and at the same time the sample sizes are less than 30. So in this case, again, technically we cannot perform the t-test. So in these cases, another approach that you can use instead of the t-test is the two-key approach. That's TUKEY, that can be found in the textbook. So the textbook provides you with a formula that you can use to compute for the confidence intervals. And there you can try to compare if the intervals overlap or do not overlap. So if they overlap, then we can't really say that they're different, but if the values do not overlap, then maybe it's clearly one average is higher than the other. So you can just try to do that, compute for the confidence intervals for the different possible pairings, and then try to see which ones differ.